All right, so we're going to skip a couple sections here, and we'll worry about similar triangles when we get back from break. But we're going to move on and continue talking about proportions. So we talked about similar polygons last time, and we've been setting up proportions to help us find different things, different segment lengths, different whatever, any type of real-world situation might have us solve. There are a couple of theorems here that offer up some more flexibility in how we see things. It's not just the triangle proportionality theorem. It's also, there's a transversals theorem and the opposite side theorem that we'll get to in just a second. The triangle proportionality theorem says this: if a line to one side of a triangle intersects the other two sides, so if a line parallel to one side of a triangle, so if we draw a line TU so that's parallel to QS, it cuts the other two sides up proportionally. And so what we're looking at here is if these two lines are parallel, then this side, these two sides are cut proportionally. So we can write some different proportions. We can say RT to TQ is equal to RU to US. Okay? Now, because of the nature of proportions, we talked about this a lot, there are some different ways that you could rearrange this proportion to still get an equivalent proportion or a true proportion. And without going through all those ways, there are some things that would have us, instead of going right to left and then right to left, we could go left to right and left to right down here. Get two ratios that we can set equal to each other and still be okay. So QT to TR is equal to SU to UR. We can go top to bottom. We can go RT to RU, QT to SU, so on and so forth. So there are some other ways of arranging this proportion. The bottom line is this: you need to establish a pattern with your first ratio here. And then the second ratio has to follow suit. Second ratio has to follow the same pattern. Okay? Now, there's a converse to this theorem that says that if you want to prove these two lines parallel, then you need to check this proportion. Here to here equals here to here. And that will do it for you. Okay? Now, what I mean by offering up some flexibility for you is that if I were to draw that picture again here, a little bit different orientation, but basically the same type of situation. The question is, what do you see in that picture? Right? I think most of you probably look at that and say, well, there's a triangle with a line drawn through it, right? And as long as these two lines are parallel, then we can use the triangle proportionality theorem. But can you also see that there's two triangles here? There is a smaller one and a bigger one. Right? There's this guy and there's this guy. If we were to name these triangles, so A, B, C, D, E. This would be A, this would be D, this would be E, this would be A, this would be B, this would be C. Now, because of reflexive property, angle A be congruent to angle A. Because of corresponding angles in those lines being parallel, angle D would be congruent to angle B. And for the same reason going the other way, angle E is going to be congruent to angle C. What that means is, without checking the side lengths to make sure that they're proportional, we've got two similar triangles. So we could do things like, we can write different proportions in that same type of picture. I could write a ratio of AE to AC and make that equal to AD to AB. The original theorem had us using these pieces to write a proportion. But the idea of these two triangles being similar says that we can match up corresponding sides AE to AC and AD to AB and still get a true proportion. Okay? So it may be that in a picture like, well, so it may be that in a picture like this, you need to see it as one giant triangle with a line drawn through it, or you need to see it as two similar triangles where you can start writing ratios amongst those sides. The bottom line is this: instead of going piece to piece, piece to piece, sometimes you might need to go whole side of a triangle to whole side of a triangle equals whole side of the small triangle to whole side of the big triangle. It's all about how you want to see it. And it's all about setting up a pattern in your first ratio and making sure the second ratio follows. Okay? How to use it? We'll take a look at this diagram. In this diagram, QS and RS, not RS, QS, excuse me, and UT are parallel. We have those measurements there. Go find RQ. So what I would challenge you to do is to write a proportion. Take a second, write a proportion, then you can start the video back up and we can talk a little bit about it. Okay. Here's what the triangle proportionality theorem says. It says you'd want to write a rate proportion of x to 9 equals 4 to 6. Cross multiply. And x is 6. So length of QR is 6. But you could also have done something like 4 to 10, because this whole big side of this triangle is 10, is equal to x2, and the side of this big triangle is x plus 9. And if you cross multiply, and solve, you still get 6 for QR. Okay? So there's a couple of different ways to see this picture, and you're going to be asked to be able to bounce back and forth between two smaller triangles and then one giant triangle with a parallel line drawn through it. Okay? Now, if we could go the other way, we can use the converse to the triangle proportionality theorem to try to show that two lines are parallel. So shoe racks, right? Some shoe racks, they have these ends and then they have shelves running in between the ends, and some of these shelves are parallel to the floor and some aren't. How can we determine that line BD, which represents the shelf, is parallel to the floor or not? Well, AE represents the floor because that's the bottom of the end sitting on the floor, and BD is the shelf. Well, AB is 33, BC is 27, CD is 44, DE is 25. Well, if those two lines are going to be parallel, then the ratio of the top piece to the bottom piece on either side would have to be congruent, had to be the same. We reduce 27 over 33 to 9 to 11, then cross multiply, and you're going to see that these two are not the same. So BD and AE must not be parallel. Okay? That's how we use the theorem to check it. There's a couple more theorems here. There's the transversal theorem. All right, so if we draw three parallel lines like these guys, UV, WX, YZ, they're all parallel. And we draw two transversals. Line L and line M are your transversals. When we do that, then what happens is the transversals get cut up proportionally. That means if I write a ratio of UW to WY, that would be equal to the ratio of VX to XZ. Okay, now, again, because of the nature of proportions, we can jump around and write the proportion in some other directions, right? And come up with different proportions. In other words, instead of going left to right, we could always go right to left. Go WY to UW equals XZ to XV. Or we can go top to bottom, top to bottom. Go wy to xz equals uw to vx. A lot of options there. At the same time, just like the triangle proportionality theorem, if you extend these transversals out, then you create more triangles. 1, 2, 3. And those 3 triangles are going to be similar also. And so you can start to patch up, you can start to piece together those sides as well. Are you using whole sides of a triangle, or are you just using these pieces that have been created by the parallel lines? That's what you have to decide. As long as your 2 ratios follow the same pattern, you're going to be in good shape. This opposite side theorem. This opposite side theorem said you have an angle bisector, and we haven't had an angle bisector in a while. Angle bisector cuts an angle in half. So if ray CD is an angle bisector, and it hits the opposite side of the angle from the angle that it bisects, then it cuts the opposite side at proportional to the adjacent whole side of the triangle. So you may not be able to see this down here, you might be able to, but basically if I write a ratio comparing AD to DB, that ratio would have to be equal to AC to CB. Okay? So we go here to here equals here to here. Okay? Kind of see that pattern? Again, it's a proportion. There are some other ways you could set this up, but that's what the theorem wants you to do. So, some examples, some practice for you here. Okay, in this diagram, angle 1, 2, and 3 are congruent. Why is that important? Well, because angle 1 and angle 2 form corresponding angles. Angle 2 and angle 3 form corresponding angles, and angle 1 and angle 3 form corresponding angles. So that's all a big, long way of deciding that all of these lines are parallel, which means that FH and CE are 2 transversals, and they're being cut up proportionally. So we need a proportion to help us find the length of HF. HF is just right here. You have some options. You can first let GH be X, and then write a ratio of X to 120 equals 300 to 150. Reduce that down to 2 to 1. Cross multiply and get X to be 240 yards, at which point HF would have to be 240 plus 120, which is 360. Okay? Or you could make HFX and then write a ratio of X to 120 equals the whole thing here, which is 450, to that bottom piece, 150. Reduce this right here. Cross multiply and get X to be 360, which is how long HF should be. 360 yards. So again, you have some options. You have some options. Okay? Last but not least, we've got an angle bisector here. They're saying that angle QPR is congruent to angle RPS. So we have an angle bisector. It's hitting the opposite side. So we need to come up with a proportion that will help us find RS. Well, the theorem wants you to go from here to here. Well, QR has to be 15 minus X. Since this whole side is 15, and that piece RS is X, QR is 15 minus X. So I'd go 15 minus X to X must be equal to top to bottom 7 to 13. Cross multiply. Right? And then you go solve and discover that RS is 9.75. And there are certainly other ways you could set that proportion up. So try it. Try to get to the answers in the homework. And if you can't, come in and see me, and we'll figure out what's going on. Okay? Homework's out in Canvas. Make sure you have that done next time.